Welcome to this explainer. Today we're diving headfirst into a really fascinating and honestly kind of hidden world of extreme engineering and infrastructure safety. When we think about massive power plants, especially nuclear facilities, we usually picture the giant reactors, the iconic cooling towers, and that vast electrical grid they power. But what actually holds all of that critical infrastructure together when the unthinkable happens? What actually stops a catastrophic failure during a massive, violent, dynamic event? Well, the answer lies in a vital yet totally unglamorous piece of technology that operates completely behind the scenes. So let me ask you, how exactly do you protect a nuclear reactor from an earthquake? Think about the immense seismic forces that threaten this critical infrastructure, or even just the severe operational shocks that can happen inside high-pressure sodium piping systems. How do you keep miles and miles of highly pressurized radioactive coolant pipes from violently shaking themselves apart? And here's the kicker. You have to do this while still allowing them to expand and contract naturally as they heat up and cool down during everyday operations. You can't just bolt them rigidly to a concrete wall, right? Because if you did, they would just snap from thermal expansion. Well, enter the snubber. You can think of it as a heavy-duty, hyper-advanced seatbelt for a reactor's piping system. When everything in the plant is operating normally, the snubber moves nice and smoothly, letting those pipes shift slowly as they heat up and expand. But the exact moment a rapid dynamic load hits, like an earthquake or a sudden violent pipe rupture, that snubber instantly locks up. It absorbs the shock and holds those massive pipes rigidly in place to prevent a catastrophic breach. It's brilliant, really. To truly wrap our heads around these devices, we have to look at the sheer scale of the forces involved. To make absolutely sure they don't fail when we need them the most, companies like Neometrics Defense Limited build highly advanced dynamic snubber shock arrestor test facilities. These testing rigs are incredible. They're designed with a load-free stiffness of 1,500 meganewtons per meter, and they can handle test loads up to a staggering 25 tons. That is 25 tons of raw force applied just to test a single device, verifying that it can actually survive the violence of a major seismic event. And getting up to those rapid dynamic loads, that takes some absolutely extreme engineering. The Neometrics testing facility uses hydraulic power packs that are capable of generating up to 300 bar of pressure. They use these high-precision servo actuators that can simulate accelerations up to 250 millimeters per second squared. They're literally recreating the exact violent forces of an earthquake right inside a laboratory just to see if the snubber will hold its ground. Now, the crucial point here is that you can't just look at a snubber and say, yeah, looks good to go. You have to meticulously evaluate how it performs under immense stress. These testing systems measure absolutely everything. They check the free working stroke to make sure the snubber actually moves without any restriction during normal temperatures. They assess the drag and breakaway force to see exactly how much effort it takes to get it moving in the first place. And most importantly, they verify the blocking speed and activation level. That's the exact millisecond and force threshold at which this heavy-duty seatbelt decides to lock up and save the reactor. All right, so because these devices are the absolute last line of defense for safe shutdowns, their oversight shifts from the laboratory all the way up to the federal level. The U.S. Nuclear Regulatory Commission, or the NRC, keeps a very, very close eye on them. The NRC mandates these really strict in-service examination and testing requirements to ensure these snubbers keep working flawlessly over their entire operational life. But, as we're about to see, having rules on paper doesn't always translate perfectly to the real world. Back in September 2013, the NRC issued Temporary Instruction 2515/189. This was essentially a massive engineering detective mission. The NRC randomly selected 10 nuclear plants, 2 from each region, plus 2 extra from Region 2, just to perform a sudden audit. They wanted to see if plant operators were actually complying with all those strict federal regulations for testing their snubbers. And what they found? It was a fascinating look into how simple administrative errors can potentially create massive physical vulnerabilities. So the audit revealed this massive web of bureaucratic confusion. The NRC discovered that plant operators were frequently getting tangled up between 2 major sets of engineering standards, the ASME Boiler and Pressure Vessel Code Section 11 and the ASME Operation and Maintenance, or OM, Code. Operators were basically mixing up the requirements for snubber examination and testing between these 2 different rulebooks. And as you can imagine, that led to some serious inconsistencies in how they were maintaining these vital safety devices. But wait, the paperwork problems didn't stop there. By law, plants have to update their in-service inspection and testing programs every 120 months to match the latest applicable ASME code. But during this audit, the NRC uncovered what we can call a technical specifications trap. Some plants were literally submitting deleted or completely outdated technical specification pages as their official Snubber test plans. Instead of building new, updated programs based on current codes, they were just falling back on obsolete documents that had already been stripped from their active plant specifications. The NRC also had to step in and issue a really strict warning regarding a specific loophole. You see, some plant operators were trying to use a section of the code known as ASME Section IWF 1230. Now, this section does allow certain general pipe supports to be exempt from in-service examination, but the NRC made it crystal clear. You absolutely cannot use IWF 1230 to exempt snubbers. No way. Because snubbers are dynamic, moving parts that are crucial for a safe reactor shutdown. They are never, ever exempt from strict testing and inspection. So why is the NRC breathing down everyone's necks about paperwork and testing protocols? Well, it's because of the invisible threats. We just talked about how these devices are built to withstand 25 tons of force and 300 bar of pressure, right? But here's the crazy part. A snubber rarely fails because it gets overwhelmed by a massive force all at once. No, it fails because of silent, microscopic degradation that happens slowly over years and years of just sitting there in a power plant. Back in 2015, the NRC put out an information notice detailing the silent killers of these mechanical snubbers, specifically focusing on grease degradation. The internal lubricants inside these devices can break down for a bunch of reasons: severe, constant vibration from the pipes, elevated room temperatures, hazardous environments, general aging. It can even happen simply because a spare snubber was pulled from inventory and installed after its grease had already exceeded the manufacturer's shelf life. And if that grease degrades, the internal mechanics just seize up and the snubber totally fails to function. Let me give you a really specific, real-world example of just how sensitive these devices are. Event Notice 51788 detailed a scary situation where a hydraulic snubber just started leaking fluid. The plant investigated and found out that the reservoir piston seal had aged prematurely because of friction heat induced by vibration. But when they took it to the lab, they found something even deeper. The seal vendor had made a really subtle material substitution. They had used a slightly different grade of ethylene propylene for the seal than what was originally approved. A microscopic change in polymer grading, and suddenly you have a leak in a vital nuclear safety device. Now, you might be thinking, hey, don't they test all of these in the plant to catch these leaks and bad grease? Well, get ready for a pretty staggering realization directly from the NRC. During a refueling outage, plants typically only select a really small sample, about 10% of their snubbers for functional testing. Because of this tiny sample size, it might actually take decades before all of a plant's snubbers are tested. In fact, some snubbers might sit in a nuclear plant and literally never be physically tested during their entire service life. Crazy, right? And that right there is exactly why physical stroking and basic visual inspections are just not enough to catch all these failure modes. The NRC realized that if you're only testing 10% of your snubbers, you desperately need a way to predict failures in the other 90%. That missing puzzle piece is service life monitoring, or SLM. The NRC insists that SLM is an integral, totally non-negotiable part of the snubber program. It's designed to track those environmental stressors we talked about and predict degradation way before a catastrophic failure actually happens. So when you bring it all together, the operational readiness of a nuclear power plant snubber system relies entirely on three mandatory pillars. Pillar 1, visual examination, just to spot obvious physical damage. Pillar 2, functional testing on those advanced 25-ton capacity rigs to ensure that 10% sample locks up exactly at the correct blocking speeds. And Pillar 3, service life monitoring. That's the crucial predictive data that ensures the invisible killers, like degraded grease and altered ethylene propylene seals, don't quietly compromise the rest of the fleet. Which brings us to the ultimate question for this explainer. We've seen the immense scale of the testing capabilities, and we've explored the really subtle administrative traps and microscopic material deviations that can take these massive devices offline. So if a snubber fails completely silently, its grease dried up and its seals degraded, and the next major earthquake is decades away, are our current safety regulations and 10% testing samples really strict enough to catch that flaw in time? It definitely leaves us reflecting on the vital, invisible work of continuous engineering compliance. Thanks so much for joining me for this explainer, and remember to keep questioning the science that keeps our world safe.